Good morning or good afternoon, where you are at, and very warm welcome from Miami, Florida to more than 400 sites that have signed in to listen to us live to our 2021 in-depth webinar.
We'll now begin with Module 1, Early ABC Projects at the Connecticut DOT. We're pleased to introduce our speakers, Tim Fields and Mike Culmo. Tim, employed by the Connecticut Department of Transportation for over 36 years, has been the principal engineer for their major structures unit within the Division of Bridges since 2013. He is the chair of ConnDOT's Bridge Standard Practices Committee, which manages and updates ConnDOT's Bridge Design Manual. Since 2011, Tim has served as the State Bridge Engineer and voting member representative on the AASHTO Committee on Bridges and Structures. He graduated with a BSCE degree from the University of Connecticut in 1984, joining ConnDOT in 1985 and advancing through multiple positions in bridge engineering. He is a licensed professional engineer. Mike is a bridge engineer with over 37 years of experience in the design of steel, concrete, pre-stressed concrete, and timber bridges. He previously was employed by ConnDOT in the Bridge Design Office for 13 years, where he designed some of the earliest uses of ABC, including the first precast full-depth bridge deck project in 1988. Mike has special expertise in the field of accelerated bridge construction technologies and constructability engineering. He is the principal author of numerous publications in the field of ABC, including the 2018 AASHTO LRFD Guide Specification for Accelerated Bridge Construction. He is a licensed professional engineer. Tim will begin today's training. Tim?
Good morning. Mike and I are going to share this presentation. Mike, as you know, as was stated, was an employee of ConnDOT during the 1980s to 1996, and is going to speak about two early ABC projects for which he had significant involvement with. So for those of you who may be unsure where Connecticut is, we're a very small state up in the northeastern portion of the United States. We've circled it right now here on this slide so everyone can see where we are. So how did we get into ABC? The spark that really started ABC was the collapse of a span of the Miami River Bridge in 1983. This is a bridge that carries I-95 over the Miami River in Greenwich. The state had not been doing a great job of bridge maintenance for several years prior to this due to some pretty significant funding limitations. However, that changed with the collapse of this bridge. An emergency bridge program was quickly initiated with wide public support. The cost for this program was a 5-cent gasoline tax per gallon. That was quickly initiated. This emergency bridge program actually addressed about 50% of our bridges. Many of these smaller bridges, and the addressing was either replacement or rehabilitation. ABC was a concept that developed out of this, out of design necessity due to limitations and the urgency for some of the need for these early projects. So the beginning of ABC in the US, this was also helped to kickstart our ABC. Some of these initiatives that are listed here were developed well after our 1983 emergency bridge program and the two deck replacement projects we're going to hear about shortly. I would say for us, Every Day Counts was probably one of the biggest initiatives that helped Connecticut deploy our ABC process here in a more systematic way. The early two projects that we did not really result in a paradigm shift. It really was around the early 2000s where ABC really took off for us. I think the Utah DOT program and MassDOT Accelerated Bridge Program were two states that we had something to learn from at that during that early time. So as I noted, the first two uses of accelerated bridge construction were in Waterbury and Seymour. Waterbury, the Mixmaster Route 8 I84 Mixmaster is a stacked interchange, and we had a major bridge rehabilitation project there addressing over 24 bridges in one construction contract, and one of those required a bridge deck replacement with a very poor detour option. The next one is Route 8 in Seymour. This occurred several years later after the Waterbury Mixmaster was well into construction, and Mike's going to speak about that. We had two bridges, one 1,000 feet, the other 1,700 feet of viaduct structures that needed bridge decks with limited shoulders. ABC with using precast deck panels became an obvious option for design, given the success that the Waterbury Mixmaster project was demonstrating. So, Mike, at this point, I'm going to switch over to you because I'd just like to know, these two projects occurred during Mike's involvement in with work at the Connecticut Department of Transportation. Mike was in state bridge design and actually fully engineered the Waterbury Mixmaster ramp, and also was guided the design of the Seymour Bridge deck replacement projects. So, Mike, over to you.
Okay, thanks, Tim. Tim and I were both junior engineers at this time in the 1980s working in this bridge program. It was an exciting time to be working at a DOT when we were literally increased our number of bridges we were designing each year from something like 10 to over 300 per year. So it was an exciting time, and we had some exciting projects. So today we're going to go through two of those exciting projects. And as Tim mentioned, these are projects that went with ABC out of necessity. So I can get the slide to advance. There we go. As Tim mentioned, we refer to this as the Mixmaster. This is a interchange of Connecticut Route 8 with Interstate 84 in the town of Waterbury, Connecticut. It's a major interchange, has 29 bridges. And in the 1980s, we did several major rehabilitation projects. The photo on the right shows what some of this looks like, and it is like a smorgasbord of bridge styles. We have steel straddle bents, concrete straddle bents, two girder systems, stringer systems. We have everything on this project, and in this interchange, I should say. But part of this project involved the replacement of a deck on one of the ramps, and it's shown in the yellow circle to the left. We'll zoom in a little closer, and here's what the bridge looks like. It's Interstate 84 eastbound to Route 8 northbound, which is a single lane exit ramp bridge. And as you all know, you go to replace a deck on a single lane bridge, it can be a challenge to do staging. In reality, you couldn't stage this thing, it was just too narrow. So we needed to replace the deck, and the only option was to close the bridge and detour traffic, and the detour was not very good. So this is where the concept of maybe looking at precast was something we needed to study. So here's a shot showing the bridge, an aerial shot. It's a 6-span bridge. It includes pin and hanger assemblies in one of the spans, so it's a complicated bridge. It is a curved bridge with straight girders, which also complicates the problem. We decided to pick a complicated one for our first precast deck, but this is the hand we were dealt in the card game. So we were given this bridge as a deck replacement, and as you can see, it's a very narrow bridge. So how did we get started? How did we get into this? And really, Connecticut DOT had been a member of the PCI Northeast Bridge Technical Committee for a few years at the time. This committee was formed in the 1980s to standardize use of precast across the Northeast. We were a member of the committee. Actually, at that time, I think it was called New England Bridge Tech Committee. At that time, we've added New York State since. We were doing a lot of work with precast box beams and slabs. They were very commonly used. So the boss who worked in our unit, Tim and I, they came to me one day and said, we need to replace this deck fast. Can you do it in precast? And my response was, yeah, probably. We'll figure it out. Let's figure out how to do this. It seemed like a reasonable solution, but we had never done anything like this before. So the way we got started was an informal research project ensued. And this is just a snippet from the research project. Actually wrote a paper for the International Bridge Conference where this is taken from, which gave a synopsis of what we researched. What's great about the United States is we share details among states. We share successes. We copy details all the time. And what we did in this research essentially was look at what was done across the country to date in 1989. And we basically grabbed all the good details and maybe set aside the ones that maybe were not so good, and we came up with a system. What's really cool about this is that a lot of the details that came out of this research are still in use today in the United States. So it was a very successful research project, and I give credit to these early users of precast who paved the way for us to do this successful project. Quick synopsis: Indiana did a precast deck on a through truss. They had all kinds of problems with leakage in the deck. They were using rubber gaskets with longitudinal post tensioning. They also had issues with seating of the panels and the stringers. They didn't sit quite properly. They had a lot of grouting that had to be done. So there was leakage too. So really, we learned from the Indiana project that some details that didn't work all that well. New York Thruway did some significant research on composite action using blockouts and shear studs, which we are still using to this day. They showed you could get full composite action. California did a project where they used the concept of leveling devices to set grade on the precast decks. So we grabbed that as well. And then Federal Highway had done research on connections of precast elements using post-tensioning, and that came in handy as well. So the conclusions from the research is that we could get composite action with blockouts. The preferred connection between panels was a grouted shear key, and that post-tensioning was a good way to connect a precast deck using a post-tensioning force of 250 psi. Which, by the way, is still in the AASHTO LRFD. So it's just some early work done by Federal Highway and others to come up with that number. And then leveling bolts combined with a grouted haunch could provide a proper grade alignment, get our profile correct. So as far as the information, we showed the photos before. It is a 6-span structure with one continuous span in the middle with pin and hangers. The deck panels themselves were pre-stressed transversely and post-tension longitudinally. We wanted a durable deck. We built this bridge in 1990, I should say the deck in 1990. We specified a construction schedule of 120 days, and we had an incentive clause in the contract, and the maximum incentive was paid out at 42 days. So that's exactly what the contractor built, which is a testament to incentives, that they hit the maximum incentive of 42 days, and the bridge was opened in 42 days. There really were no construction problems. I actually went on vacation one of the first early weeks of the project. This is before cell phones. I think I might have had a pager at the time, and it may be before that, but I never got a phone call because I came back from vacation and they were already on span 3. So it really did work out well. Again, a testament to the details that we gathered from around the country. Here's some of the details. This is back in the early days of CAD. Again, we're all probably familiar with some of these details, and it really hasn't changed much in the last, in this case, 30 years. One thing we did learn from our experience with adjacent box beam bridges is that if you take 10 4-foot wide adjacent box beams and lay them out side by side, you will not get 40 feet. It'll be usually more than 40 feet because of the tolerances, things like sweep tolerance and flat tolerance of a precast concrete deck element. So we learned from that and decided that we needed to have a system that had adjustability built into it. And the way we handled that was having closure joints or closure pores at the end of the span to accommodate what I used to call dimensional growth of laying out a number of panels. And that adjustability was key in the success of this project. This bridge was curved, so these panels were actually shaped trapezoidal. And we had 3 different styles of precast with the blockouts in 3 different patterns. And so the actual blockouts would stagger across the top flange as you went across the bridge. And it made it easier to fabricate as we had very similar panels. As far as details, some of these details are not in CAD, but you can see the longitudinal post tensioning using an oval duct that was used. The parapet, we decided to go with a parapet that was extended over beyond the edge of the deck panel to just give a nice clean edge to the outside of the bridge. And again, the shear connector pockets are pretty standard to even use today. So some photos of the construction. These are kind of grainy photos because they're really old. You can see the date on them, 1990 construction, and the contractor used timber decking to catch debris because there are roadways below the bridge and actually a pedestrian walkway below the bridge. And you can see the demolition was complete in this photo. And then erection of the deck panels progressed very smoothly. If you look at it, it looks like this thing is not very flat, and the answer is it is not very flat. This deck is actually on a 7% grade going downhill. So there was concern the panels would slide. The contractor put some blocks to keep the panels from sliding around, which was really not a problem. But you can see the post-tensioning blockouts for the connections of the post-tensioning duct, and the parapets were cast in place. As you can see the rebar coming out of the panels. You can also see the leveling devices sticking out of the top of the panel. Again, a detail that's fairly common today. As far as post-tensioning, following the erection of the panels, the transverse joints between the panels were grouted, and then post-tensioning was pushed through the tendons and tensioned one strand at a time. Pretty simple. I call this post-tensioning 101, very straightforward post-tensioning, and it took about 2 days per span to both install the tendons and tension them and grout them. Following that, well, this photo on the left shows grouting the joints, which was done before the post-tensioning. And the photo on the right is one of the closure joints at the end of the span. It seems like an awfully wide closure joint, but that was actually above a pin and hanger assembly. We couldn't run the precast over the pin and hanger assembly because of the plates that were involved in that. But one thing you'll notice, though, all this post-tensioning and grouting is done before the shear connectors were installed. We didn't want to induce a positive bending moment into the structure by having post-tensioning be applied after composite action was made. So up until the post-tensioning, this slab was essentially floating on the leveling bolts prior to the grouting of those blockouts for the shear connectors. Here's a photo of the completed bridge. Again, a very grainy picture of some very old cars driving across it. I love these photos, just showing the age of the bridge. Again, built in 1990, and really it went very smooth. We had no real issues with the structure at all. Again, a testament to the quality of details that we gathered from around the countries and the people who came before us. So I went back after 20 years. These photos are after 20 years in service. It's now been in service for 30 years, and we know it's in the same condition today. And the key thing we were looking at is leakage through the joints, and there is none. We did use a membrane waterproofing system and asphalt overlay on this bridge, and then combined with the quality of the post-tensioning and the grouted keys and the wear-in surface and the waterproofing, we're not getting any leakage through the joints. The photo on the right looks like there might be some staining. That's actually overspray from the painting that occurred after the deck was placed. So really, we had no issue with this bridge whatsoever, even after 20 years of service, and it continues to be in the same condition today. So we're really getting durability out of these structures. That was the first project. So we move on to our second project. We had such good success in the Waterbury project that now we said, let's take this thing up a level or a notch or two. And this is a very challenging project. This is my hometown of Seymour, Connecticut, which has two very long viaduct structures that run through the center of town. They're curved structures. They're all simple spans. As Tim mentioned, the South Bridge is 1,000 feet long with variable width with ramps, acceleration and deceleration lanes on it. That's the photo on the bottom. Photo on the top shows the northern span, which is 1,700 feet long. Again, a curved structure, all simple spans. But it is luckily that bridge, the roadway is parallel through there, so we didn't have the variable width. Again, all simple span structure, and we needed to replace the deck on these two bridges. So the challenge is that we wanted to go with weekend construction only. As you remember, the first bridge took 42 days to do 6 spans. We figured, looking at that success, that we could actually replace a span in a weekend using this system. And that was the challenge. And the challenge was to close half the bridge every weekend and have the contractor give one half of the structure to the contractor each weekend. And you had to really work from top down because access, as you can see from below, was rather difficult. This is location plan showing where the bridge is. As Tim showed before, it's in southwest Connecticut. So the approach, again, to build on the successes of the I84 bridge, we use very similar details. The key was to close one direction Route 8 and give the contractor one whole side of the structure each weekend. The bridge barriers were cast after the weekend. The idea was that we put temporary barrier in the shoulders, reopen the bridge on Monday morning, and then work on the barriers during weekday off-peak times, like at night when traffic was low. This saved a significant amount of time. Not having to cast barriers made a big difference in the weekend work. The contractor, to meet the project schedule, had to do multiple spans per weekend, and they were doing up to, I believe, 3 spans per weekend when they got rolling. And this bridge was built in 2 construction seasons, one for each direction of the highway above. A couple details showing the staging. Again, we did a crossover and put one lane in each direction on half of the structure, and then gave the contractor the other half of the structure. And you can see the hatched area is the precast section that was put in. Temporary barriers were put in place on Sunday night, and that was the work area then was reopened to traffic on Monday morning. So we drove on the precast panels for the entire first year, and at the end of the season, the entire span was waterproofed and waterproofing was put on, and asphalt overlay was put on at the end of the season. Just a plan showing some of the details as a couple things that we added to this project that were not involved in the Waterbury project. We had a roadway crown on some of the sections, so we ended up using longitudinal closure joints, which I can pick up with the pointer here. We have these longitudinal joints running the length of each direction. There's a open joint in the middle of the structure, but basically we added a crown detail to handle the roadway cross slope. The parapet details were similar to Waterbury. Again, those parapets were cast after the weekend construction. So the second panel project was another complete success. It was a very challenging project. Contractor did a wonderful job working this project to get it done in time. There were no significant issues. There were a lot of little minor issues like any project of this sort. Anytime you turn up the heat from a 42-day project to a 3-day project, you can imagine there's a lot more pressure on the contractor, but it was a successful project. We also have looked at the inspection reports for this bridge, and it's doing very well as the Waterbury Bridge. So we learned a bunch of things in these first two projects. One, that we could build things very quickly. Two, precast concrete could be used for bridge construction. And three, what we learned more than anything is the use of quality details were so important to get excellent service life out of these structures. And seeing these structures in service for 30 years now, the condition, we have no doubt these structures, these decks will last. My feeling is they will last 75 years, the full life of the structure, because we really are seeing really quality durability out of these two structures. Again, the key is it's always good details. I'll turn it back to Tim now to finish up this presentation.
Yeah, thanks, Mike. And I think one thing that provides great service life with our bridge decks here is the use of membranes and overlays. That was instituted as standard practice in the late 70s here, mid to late 70s, and our bridges that have been built with waterproofing membranes, those decks have performed very well for us. So the current ABC program development, these two early examples here help to pave the way for later work that followed. In Connecticut, we never had a problem here with upper management resistance to ABC, accelerated bridge construction. It had really been favored. It was kind of an incremental process, though. After Mike left the department in the 1990s, I would say there was probably a little bit of a lag in the full implementation here and push to use accelerated bridge construction on a more routine basis. Another aspect of this is cost, and we really haven't, in these two examples here, we didn't discuss cost per se. ABC typically is going to cost a little bit more in upfront costs and construction costs, and as you're going to hear in later presentations, there's some savings that typically would go with ABC with much shorter contract durations. So again, our early program was done without a decision matrix. The decision matrix, which you're going to be presented in the following presentation, is a tool that we developed to help objectify the decisions to go with ABC or not. And right now, I think another key for these ABC projects, and you'll hear again on this, is getting the buy-in from our stakeholders, because typically, like in the Seymour project and the Waterbury project, when you take ramps out of service in Waterbury for any period of time, there's a cost to pay for our users and detour around We didn't show you the detour there, but it was a lengthy detour and the Waterbury ramp replacement. Seymour also had, I'm sure, highway impacts during those weekend closures for 2 years. I'm sure there were buildups, but with traffic buildup. But one of the keys here, and you'll hear more about this, is people, once they understand what's on the table, adjusting their schedules to help reduce traffic loads. So at this point, I think we're going to conclude this presentation for Module 1 and take any questions.
Thank you, Tim and Mike, for your presentations on the early ABC projects at the Connecticut DOT. Very interesting and great history there. I'd like to now turn it over to Paul Lyles, former Georgia State Bridge engineer, who will be moderating the Q&A sessions, assisted by Ahmed Abu Hawash, Chief Structural Engineer with the Iowa DOT, both of whom are members of the ABC UTC Advisory Committee. Paul?
Okay, Mary Lou. Yeah, this is Paul. There are a few questions here. The first one we have is, what were the lessons learned from your first precast deck panel projects?
Yeah. Okay, maybe I'll start with that. I think, some of them I covered in the presentation, but I'll reiterate them because they are important. The first thing I remember, literally, I remember talking with the design crew, and the first thing we talked about was we have problems, not problems. We're aware of when you would put adjacent precast panels together that you get issues with dimensions and growth. And so our assumption going into the project is nothing is perfect, nothing is exact, and we need to account for that in our design. So the key things was to account for tolerances in the elements by having joints between the elements that were adjustable, and to have closure joints at the end of the bridge to adjust for growth of the overall length of the deck, and then to have a haunch with leveling devices so we can set profile grade perfectly. The early projects, especially in Indiana, they had issues with both of these, getting the panels to seat properly, getting the proper grade. And we just learned that we needed to have adjustability built into the system. And again, I'll just say the details we took, we didn't invent many details for this project. We were standing on the shoulders of people who had done work before us, and we just put together a system based on the early work done in other states to come up with a system that had adjustability and had details that were proven to be durable. And that's the key to success. The key to success is always detailing. It's detailing, detailing, detailing.
Okay, Mike. So, I mean, do you still use the same details today?
Yeah, we do.
Yes.
We are kind of moving away from post-tensioning with the advent of UHPC now. It seems to be becoming a more popular thing in the United States. But in the Connecticut, you're going to see later on, we'll talk about another more recent project, which it's basically the same details. So, yeah, the answer is yes.
Okay. Here's a question that came in during the presentation. For Seymour Viaduct, was the asphalt wearing surface removed on the entire bridge prior to replacing spans, or was the new deck set at the same elevation as existing wearing surface to allow traffic flow during the week?
Wow, that's getting down in the weeds. I can't recall. Yeah.
I would think we would have had to been bare, Mike. Oh,
I think so too. I think they stripped the deck before we started, or they might have ramped down. Honestly, Paul, I can't remember. It's a long time ago.
Yeah, that would have been a pretty significant drop off between the overlay and the bare deck. So I'm guessing we would have stripped that down. That would have been common to do at that time, and that's typically how we would do a bridge if we were just doing a deck patch membrane overlay project.
Now, one thing we did learn, though, is we did drive on the bare deck for the first season until the end of the season. And we found out very quickly that if you were to use a bare deck, you'd have to do diamond grinding because it is a rough surface. So we drove on essentially a washboard for the first portion of the project. But I always call the overlay is also your last tolerance adjustment when it comes to profile. If you got a rough surface, the paving makes everything nice and smooth. So, yeah, we learned that, too, that if you were ever going to go to a bare deck, you'd have to do diamond grinding.
Okay. Here's one that came in as the pre-webinar question, and this kind of leads into our next thing, but it says, how was the ABC program initiated? I think you kind of mentioned that with these two projects. And they said, is there dedicated funding for the ABC program? Now, you mentioned the 5-cent gas tax. Is there any other funding, and is that tax still in place?
That tax is not in place per se. I would like to say our ABC program has been basically the incorporation of ABC decision making in our projects here. So we don't have a dedicated program just for accelerated bridge construction. Accelerated bridge construction is a design alternative that's explored during preliminary design. So, our program per se is basically the encouragement that we offer, that we provide, that's supported by upper management here at ConnDOT to seriously consider accelerated bridge construction in all projects now that involve deck replacement, superstructure replacement, or entire bridge replacement. In Connecticut, we have very high, traffic densities on our highway systems, and that means there's not typically shoulders to move traffic to on major highways, major bridges, I would say, that are in the 1960s vintage. Many of those have inadequate shoulders to carry traffic while working on the bridges, and it's not just true for the interstates, it's true for many bridges of that vintage. So Connecticut goes to great lengths to try to accommodate especially our weekday commuters. We've gotten a lot of grief where we have not done that. So I think accelerated bridge construction has worked hand in hand in trying to mitigate traffic impacts, construction impacts on our highway users, particularly during peak travel hours.
Okay. We're almost out of time. I'm going to ask Ahmed if we've got any questions that came in after we started the question and answering. Ahmed?
Yeah, Paul, we do have a few questions. Were any issues with the deck panels laying on multiple girders in terms of weight distribution?
Great question. And we were concerned about that. And leveling devices actually serve two purposes. One is they set grade, but they also do deadlift distribution. So we had a specification that required the torque on the leveling bolts. I believe they all had to be within 15% of each other. So between keeping the torque relatively equal and the cross frames on the bridge, we felt that we were getting proper deadlift distribution. It's a good question.
Okay, thanks, Mike. We have time for one more question. Assuming that the post-tensioning was done first and the blockout were grouted, what are the advantages and disadvantages of post-tensioning after grouting the shear stud blockouts?
Okay, I'll take that too. That's something we consider during design development. Obviously, and every time we do one of these decks, the contractor asks, they want to grout everything first and then do post-tensioning later. What that does is it induces essentially a positive bending moment into the superstructure because of the eccentricity of the post-tensioning with respect to the neutral axis. So obviously, in most cases, that's not going to be desirable. Sometimes you can get it to work. Maybe we've talked about doing that for continuous spans and negative moment regions to actually get a positive bending moment. But in reality, in most cases, we do want to do the post-tensioning before composite action is established, so we don't induce that positive bending moment.
Thanks, Mike. I think it's 40 after the hours, the starting time for the next module.
Thank you, Paul and Ahmed. We're at the end of the first 40-minute module. Thanks again to Tim and Mike for presenting Module 1.